When an engineering project reports 70% progress, what does that number actually mean? Does it mean that 70% of the budget has been spent? Does it mean that 70% of the planned duration has elapsed? Does it mean that the engineering team feels the work is almost complete? None of these interpretations is reliable. Engineering progress must represent physical work completed against a clearly defined and properly weighted scope. If you cannot explain how a percentage was earned, that percentage is not progress. It is an opinion presented as data. Accurate progress measurement gives project stakeholders two critical answers: where the project stands today and where it is likely to finish in terms of schedule, cost, resource demand, and deliverable readiness. Weak progress measurement hides emerging delays. Strong progress measurement exposes them early enough for corrective action. This is why engineering managers, discipline leads, designers, and project controls personnel must report progress honestly. Optimistic reporting does not protect the project. It only postpones the recognition of problems until recovery becomes expensive, disruptive, or impossible. The fundamental principle is simple. Progress is earned by completing work. It is not earned by consuming hours. It is not earned by attending meetings. It is not earned because time has passed. It is not earned because the schedule says the activity should be complete. The most practical method for measuring engineering progress is based on budgeted and earned man-hours. Each measurable activity is assigned a budget. That budget establishes its relative weight within the project. As physical work is completed, a corresponding portion of the budgeted man-hours is earned. The basic calculation is straightforward. Earned man-hours equal physical percent complete multiplied by budgeted man-hours. If a drawing has a budget of 100 man-hours and has physically reached 40% completion, it earns 40 man-hours. If another deliverable has a budget of 500 man-hours and reaches the same 40% completion, it earns 200 man-hours. The second deliverable contributes more to overall project progress because it represents a larger volume of engineering work. Total progress is calculated by dividing total earned man-hours by total budgeted man-hours. Suppose a discipline has 6,000 budgeted man-hours and has earned 2,400 man-hours. The measured progress is 40%. The calculation is simple. The real challenge is determining whether the claimed physical progress is genuine. This is where rules of credit become essential. Rules of credit divide a deliverable into predefined and verifiable stages. Each stage carries an agreed percentage. Progress can be claimed only when the stated condition has been achieved. Consider an engineering drawing. Credit may be distributed across CAD setup, engineering development, initial drafting, internal review, customer review, and final issue. A drawing is not 90% complete simply because it looks almost finished on a screen. It earns progress only by passing the agreed maturity gates. A typical engineering drawing may earn 5% for setup, 25% for engineering, 35% for initial drafting, 10% for internal review, 10% for customer review, and 15% for final issue. A P&ID may earn progress through CAD setup, process engineering, initial drafting, internal review, customer review, design review, or HAZOP and final issue for design. A datasheet may earn progress through application review, preparation for internal review, customer review, issue with the requisition, and final conformance. A requisition may earn most of its credit during technical development, followed by checking, issue to procurement, technical bid evaluation, and final issue. The exact percentages may vary from one project to another, but the principle must remain consistent. Progress must be tied to demonstrable maturity, not personal judgment. This protects the project from the dangerous, almost complete condition. Many engineering deliverables reach 80 or 90% quickly and then remain there for several reporting periods. Why does this happen? Because the final portion often includes checking, interface resolution, customer comments, certified vendor information, design review actions, construction requirements, and formal issue status. Poorly designed rules of credit assign too much progress to early drafting and too little to checking and closure. The project then appears healthy during development, but suddenly slows near completion. Good rules of credit reflect the true distribution of effort, maturity, and risk across the entire deliverable lifecycle. For production-oriented engineering activities, the preferred approach is the earned work unit method, also known as the incremental milestone method. You develop a detailed task list, assign budgeted man-hours, define measurable milestones, and status each task according to actual work accomplished. Earned man-hours are calculated at the task level and then rolled up through the activity, discipline, area, subproject, and overall project structure. This method is effective because the reported progress is connected to specific deliverables and identifiable work units. However, not every engineering activity produces a drawing, calculation, model, or document. Engineering management, project coordination, field support, procurement follow-up, and some construction support activities are continuous and time-dependent. These activities may be measured using the level of effort method. Level of effort progress is generally calculated by dividing expended man-hours by forecast man-hours at completion. But this method must be used carefully. Level of effort measures the consumption of a continuing support service. It does not prove that a physical deliverable has advanced. If you apply level of effort to production engineering, an inefficient task can show increasing progress simply because more hours have been spent. That destroys the integrity of the progress system. The distinction must remain clear. Use earned work units for measurable production activities. Use level of effort only for genuine support activities that cannot reasonably be measured through quantities, milestones, or deliverables. Several standard rules must govern the system. First, percent complete must come from physical work accomplished. Second, the progress budget must equal the approved estimate plus approved changes. Third, every budgeted item must be included in the measurement system. Fourth, earned man-hours must equal approved physical progress multiplied by budgeted man-hours. Fifth, total progress must equal total earned man-hours divided by total budgeted man-hours. Sixth, progress must not be changed by actual expenditure, forecast values, or productivity performance. This last point is frequently misunderstood. Imagine that a task was budgeted for 100 hours. The team has spent 120 hours, but only 50% of the physical work is complete. The task has not earned 120 hours. It has earned 50 budgeted hours. The additional expenditure may indicate low productivity, underestimated complexity, rework, late inputs, or poorly controlled scope. It affects the forecast, but it does not create progress. Now consider the opposite situation. If the team completes the same task using only 70 actual hours, the task still earns the full 100 budgeted hours at completion. The underrun indicates better productivity. It does not change the definition of progress. Budget establishes weight. Physical completion earns progress. Actual expenditure measures resource consumption. Forecast predicts the final outcome. When you combine these four concepts incorrectly, management loses the ability to distinguish progress from productivity. Other progress methods may be used in selected situations. The straight line method earns progress in proportion to elapsed duration. If 2 weeks have passed in a 5-week activity, the reported progress is 40%. This method is easy to apply, but it assumes that work progresses uniformly with time. Engineering work rarely behaves that neatly. Use the straight line method only when duration is a reasonable representation of work accomplished. The 50-50 rule earns 50% when an activity starts and the remaining 50% when it is completed. This method is suitable only for short duration activities, generally 2 weeks or less. When it is applied to long activities, it creates artificial early progress and hides unfinished work. The nonlinear method uses an S-curve or another planned distribution. A 70-30 relationship may indicate that 70% of the duration is required to complete the first 30% of the work, while the remaining progress occurs later. This method can be useful when the effort pattern is genuinely nonlinear, but the selected curve must reflect how the work will actually mature. Progress can also be earned in blocks against predefined milestones. A fixed number of budgeted hours may be earned when a formal review, submission, approval, or design gate is completed. Whatever method you use, it must be objective, agreed before reporting begins, and applied consistently throughout the project. Now consider 3D model progress. A 3D model can create the illusion of rapid advancement. A model may look visually impressive while still containing preliminary dimensions, incomplete engineering, unresolved clashes, missing supports, and unverified supplier information. You cannot measure model progress by appearance. Before modeling begins, the project must establish the work breakdown structure, model weightings, measurable discipline components, reporting tools, and progress reporting format. Each model, area, or task must receive a WBS identity and a budgeted hour weighting. Structural modeling may be divided by plant area and individual model. Piping may be divided by area, unit, model, and line number. Equipment may be measured by tagged item. Civil progress may be measured by complete models or by identifiable components such as foundations, roads, pits, and underground systems. Electrical modeling may be measured through cable ladders, raceways, tagged equipment, and underground systems. Instrumentation may be measured through tagged instruments, supports, junction boxes, panels, and model areas. The level of breakdown must match the level of control required. Excessive detail creates an administrative burden. Insufficient detail hides performance problems. 3D model progress normally rolls upward through several levels. First, assess the progress of each measurable component. Second, calculate the weighted progress of the model containing those components. Third, combine the weighted models to determine discipline modeling progress. Fourth, combine discipline results to determine total modeling progress. Fifth, integrate modeling progress into the overall engineering progress system. The calculation follows the same earned value principle. Earned weighted value equals component progress multiplied by its budget hour weight. Total model progress equals the sum of earned weighted values divided by the sum of model weights. Suppose one structural model has a budget weight of 150 hours and is 72% complete. It earns approximately 108 weighted hours. Another model has a budget weight of 140 hours and is 25% complete. It earns 35 weighted hours. You repeat this calculation for every model, add the earned weighted hours, and divide the total by the combined model budget. A large and complex model must contribute more to discipline progress than a small and simple model. An unweighted average would treat both models as equal and produce a misleading result. Rules of credit must also be defined for every modeling discipline. A piping line may progress through preliminary routing, detailed modeling, clash checking, stress analysis incorporation, support completion, back modeling, and final readiness for construction. An equipment item may progress from preliminary outline and nozzle placement to certified supplier data incorporation, checking, clash clearance, and readiness for drawing extraction. Structural modeling may be assessed through primary steel, secondary steel, tertiary steel, engineering checks, model review, clash resolution, and drawing extraction readiness. Civil modeling may progress through data collection, model development, checking, model review, change incorporation, and preparation for drawing extraction. Electrical raceway progress may include design requirement review, routing, support location, checking, model review, comment incorporation, and extraction readiness. Instrumentation modeling may include instrument location, support location, checking, model review, comment incorporation, and preparation for drawing extraction. The rules must reflect engineering maturity, not only graphical completion. Subjective assessment may still be required, particularly when individual components are difficult to count or when the final quantity remains uncertain. Pipe supports are a good example. Measuring every support individually may require significant effort, while the final number of supports may continue to change as the design develops. In such cases, structured engineering judgment can be used, but it must be anchored to agreed maturity conditions, estimated quantities, model quality, and the availability of reliable design information. Subjectivity should support the measurement system. It should never replace it. Model review sessions can also provide evidence of maturity, particularly in relation to layout, access, operability, maintainability, constructability, and clash resolution. However, attending a model review does not automatically justify full review credit. Actions must be recorded, assigned, resolved, and closed. A model is not complete because the review meeting has ended. A model is complete when the agreed completion conditions have been satisfied. The reporting process must also define clear accountability. Engineering and design teams assess task-level physical progress. Discipline leads validate the assessment and confirm that the claimed percentage reflects actual maturity. Project controls compiles the approved data, performs the required roll-ups, checks consistency, and prepares summary reports. Engineering and project management review trends, variances, constraints, and forecast consequences. Project controls should not invent engineering progress. Engineering teams should not inflate progress to protect appearances. Management should not pressure disciplines to claim progress that cannot be supported by evidence. Each group owns a different part of the control system, and the integrity of the report depends on all of them. You must also investigate unusual reporting patterns. If actual hours are increasing but earned progress remains flat, examine productivity, rework, delayed inputs, interface problems, and scope growth. If progress increases rapidly without corresponding deliverable issues or model maturity, review the earning rules. If a discipline remains at 90% for several reporting periods, identify the unresolved closure activities. If model progress is high but drawings are late, examine extraction, checking, annotation, and issue processes. If physical progress appears advanced but procurement or construction cannot use the output, question whether the selected milestones represent usable completion. The purpose of progress measurement is not to create an attractive dashboard. Its purpose is to provide an early warning system. A credible progress system tells you what has been completed, what remains, where productivity is failing, where engineering information is constrained, and where the completion forecast is becoming unrealistic. The final requirement is honesty. A lower but defensible progress figure is more valuable than a higher percentage built on optimism. A reliable 48% gives management a basis for action. An artificial 65% creates false confidence. When you define measurable scope, assign rational budget weights, establish realistic rules of credit, separate progress from expenditure, and roll the results through a disciplined WBS, engineering progress becomes traceable, auditable, and actionable. That is the standard you should demand. Do not ask what percentage feels right. Ask what physical work has been completed, what evidence proves it, what budget weight does it carry, what must still happen before the deliverable becomes genuinely usable. That question transforms progress reporting from an administrative routine into a project control system. Once your project can answer it consistently, you are no longer managing engineering through assumptions. You are managing it through evidence.